out. And so I actually verified that, in fact, this made your grade better, or at least it didn't make it worse. And actually everybody in the class improved. Probably some people improved by a lot, some people improved by little, and that's also probably because of the way some of you actually answered the questions. It said some questions actually said, write this in interval notation, and your answer was actually with less than or equal signs, and so that's sometimes where problems came from. So, anyhow. The one thing I would probably want to we went for a joyride. Okay. The one thing I probably should say, and I'm gonna reiterate this just to have it in mind, is the fact that if you in fact scored like below 40%, then you probably need to figure out exactly what your best case scenario is. You could probably come and see me and figure out exactly why you scored 40%, below, in the sense that I scored that because I didn't really know the material, or I got confused, or I didn't really do a review, and now I actually did a review and understand things a lot better, and things of that nature. But in the end, I guess it's the ball is in your court at this point, as is in to figure out where you're actually situated. So, do you have any questions? Does everybody understand? Did everybody understand what I handed out? Because some of you actually came in late. So there's 3 numbers there. Let me repeat that. The first and the second are actually the same. The third one is the percentage that you scored. So the first one is actually out of the first 2 numbers, whatever, are how many points you got out of 50, and that actually worked out quite easily, considering I was grading 25 questions. So technically, all I had to do is just double your score that you got afterwards. Okay. And also I should probably point out that I showed this to you on Friday, but if you have questions in the sense that you want to actually see how you were graded or anything like that, I did bring with me the the spreadsheet of all the questions that you got. So if you want to see where I gave you points or not, you can obviously come and see me, and we can talk about that. I didn't want to repeat writing 34 questions for each individual person, and trying to cut that into pieces and give it to you would be, well, not too much fun. Okay, so questions. As I said when we left off on Friday, I pretty much expected you to start working, on section 1.1, because most of the stuff you actually have done in the past, or we actually more or less reviewed it. So let me just go more or less page through page and figure out if there's anything that I need to add additionally. So as the first part of the section 1, it was the definition of a function and the graphs and everything else. Well, we already talked about functions up to this point, so I don't necessarily think that there's any need in talking more about that. The next topic was domains of functions, and do I need to talk about that in general, domains of functions?
Can you go over it just real quick?
Okay, so in general, the domain of a function is by definition, I guess I should probably write it out. So it's the set of all real numbers for which f of x makes sense. It's not really a very scientific definition, but that's basically what the essence of the definition, this is what it captures. So the idea is you're looking for all possible values, and I said it on purpose in words here so it actually comes out and say it's all real numbers, and so you don't just look at integers or look at rational numbers or anything else. And the idea is domains will always be actually intervals. Okay, I mean, yeah, technically I could define a function that's actually defined on just integers or just points or whatever, but the idea is you're actually looking at intervals when you come up with definitions. So, what do we know? Well, if we look at any polynomial function, that by definition has a domain of all real numbers. Is there anything that I can't put in a polynomial? And the answer is no, right? Why? Because there's really no restriction, right? I can take any number, raise it to any power, multiply it by a number, add it to another number, I'm still going to come up with something, right? And so the idea is, if you look at polynomials, and maybe this is actually something that I should have talked about as we move along, because section 2 deals with types of functions. But anyway, if you look at polynomials, the domain would be all reals. If you look at rational functions, which is actually what you had in the test, what is the only condition that has to be satisfied versus everything else? What are rational functions, by the way? Rational numbers, not radicals, but rational. Think about rational numbers, rational functions, think about rational numbers. It's a ratio between two things, right? And so a rational function is actually defined to be a ratio between two polynomials, right? Now, since polynomials are defined everywhere, the only condition that you have to satisfy as far as the rational function is concerned is you can't divide by 0, right? Does that make sense? And so the only thing that you actually have to take into account is, when is the denominator 0? Well, those are the only points that you actually have to exclude, which is, again, what you had as far as the quiz, the pretest was concerned. What else? I guess the next topic would be radical functions, right? What has to happen as far as radical functions are concerned? Well, the idea depends on what type of radical functions I'm looking at. So if I, for instance, look at f of x equals the square root of x, what would the domain be for that? Not only all positive, but actually all non-negative. Why? Because the square root of 0 is 0. It doesn't say that my function can't be 0, right? And so the idea is we're looking at everything from 0 on. Does that make sense? Okay. However, how about if I look at f of x equals the cube root of x? The domain is all real numbers. Does that make sense? Is everybody understanding why? Yes? Because the cube root of negative 8 is in fact negative 2. Why? Because negative 2 cubed is negative 8. Okay? Cubed roots, any odd power, the minus, stays there, which means that I actually am looking at the entire real axis. Does that make sense? Okay, another set of functions, and it's, as I said, it's probably not necessarily good that I'm going in this direction, considering 1-2 actually will talk about types of functions, so we'll probably maybe just skip part of 1-2 that talks about functions. The next type of functions that we actually talked about would be trigonometric functions. Now, we spent a good amount of time talking about trigonometric functions, right? What is the domain of sine? What is the domain of cosine? All real numbers, right? Think about the graph. It just oscillates, but it keeps going forever, right? What is the domain for tangent of x? So if I look at f of x equals sine of x, or I look at f of x equals cosine of x, then their domain is just all real numbers, right? So now what happens if I look at f of x equals tangent of x? It has asymptotes technically every pi, but it's at pi over 2's, multiples of pi over 2. right? Does that make sense? Remember what the graph of tangent is, and we talked about this before, right? Right? The idea is, it has these vertical asymptotes, but as it turns out, the graph keeps repeating itself, right? It's a periodic function, which means it'll go forever, right? So how do we say that in words? How do we write the domain for this function? Because keep in mind, if I ask you for the domain of the function, and you say minus pi over 2 to pi over 2, you're only telling me just a little bit of the domain. You're not actually saying anything outside of that. How about tangent of pi? Well, that's clearly defined, right? Tangent of pi is just 0. Right? Well, that doesn't show up in the domain. Right? So how do I write the actual domain? Who's lost? K is an integer. This is z. I guess I'm writing it in a bad way, right? So this just says K is an integer. Why is this definition making sense? When K is 0, this is just pi over 2. Well, it clearly can't be at pi over 2 because that's a vertical asymptote, right? When K is negative 1, this is pi over 2 minus pi. That's going to be negative pi over 2. That picks up this term. When K is 1, this is going to be 3 pi over 2. It'll pick up this asymptote, and so forth. This is basically exactly what you just said in words. We said it starts at pi over 2 and it's a multiple of pi, right? It goes every pi. Well, that's basically what I'm writing here. It goes off every pi. Does that make sense? Yes? On the same token, and I know for a fact you've done this in pre-calculus, but on the same token, if I say solve, and this is obviously nothing to do with section 1, but since we brought this up and since everybody looked at it very confused, let me just write it out. Solve sine of x is equal to 1/2. What is x?
Square root 2 over 2.
Sorry?
Square root 2 over 2.
It has to be an angle.
No.
Right?
Pi over 4.
Sine of what angle is 1/2? Pi over 6? So what is my answer? Can it be anything else but besides pi over 6? What else can it be? Well, if you look between 0 and 2 pi, you'll come up with pi over 6, and you'll come up with 5 pi over 6. Right? There's 2 points. However, sine is a function that has a period of 2 pi, which means every 2 pi, that, basically what this says, again, k is an integer. Again, when k is 0, you just pick up pi over 6. When k is 1, you pick up 13 pi over 6, and so forth. Is everybody understanding this? Yes? Okay. All right, so let's see. Before I go any further, do you want me to do any problems from 23 to 27? 23 to 27. So basically, what I usually like to do, because I guess I got so preoccupied by this pretest the first week of class, I never really told you exactly what I'm usually doing when I'm teaching calculus. And I do this in the hopes that it actually helps students try, get better at things. I very seldom actually go through the examples in the book. I figure they're already solved. So unless there's actually a reason why I should go through it, in the sense that they're really trying to capture a concept that I really want to stress at you, at a particular concept, then I usually don't go through the examples in the book. I figure, what's the point? You can actually read them yourself at home and get an extra helpful hint. So what I usually do, since the homework is always going to be even problems, I usually just go directly to the section and pick some odd problems, or you can pick whatever odd problems you want me to do, and that way it kind of, instead of doing the actual example, I do one from the end of the book, which means if you go home and study, you should have more than just one particular type of that problem. You can look at the example, you can also look at what I've done in class. Is that making sense? And so that's why I said, which problem would you like me to do? 23, 25, 27, or would you like me to do any of them? Because that's problems involving domains, and we just basically talked about domains. So, do you want me to do any of them? Or is this something that you understand and we move on? And don't answer all at once.
23.
23? Okay, so the idea is we have... Okay, another thing I should probably point out is that in general, this is the way I write problems, and we'll get used to this, I think, as the semester progresses. It just says problem 23 on page 9. Okay? So f of x is equal to x divided by, what is it, 3x minus 1? 3x minus 1. Let's see, can I move this? So, the question asks, can you find the domain of this function? Which type of function is this, just looking at it? Rational function, right? It's a polynomial over a polynomial. What did we say about rational functions? You can divide by 0, everything else goes, right? So what do we have to do? 3x minus 1 is equal to 0. Means x is equal to 1/3. And so your domain then is going to be minus infinity to 1/3, union 1/3 to plus infinity. Yes?
If you get, like I solved 24 and I got like two different numbers that cannot be x. Is that when you do the like negative infinity to like -2 and then negative, you pick it up and then you have another one?
Yes, so you'll have 3 intervals. The one thing I should point out, and I've seen this on your tests, and I want to make sure that I bring it up. The real axis works. How does the real axis work? You start basically at minus infinity. You keep basically going up, but in the sense that you're actually decreasing as far as the numbers are concerned, to 0, and then you have positive numbers, right? When you write your solution, you always have to make sure that you write it from the smallest number to the highest number, okay? And I've seen this in some of your tests, and I want to make sure that I actually bring that up. So let's say my problem is of the nature 1 over x minus 3 times x plus 3. I don't know, x plus 2. Let's make it a little different. So then x cannot equal 3, and x cannot equal -2, right? -2 is less than 3. So when you write the domain, it's going to be minus infinity to -2, union minus 2 to 3, union 3 to plus infinity. Does that make sense? The idea is, this is how you read them. One thing that you can't have, and I've seen this on some of your tests, -2 to minus infinity makes no sense. Is everybody understanding why it makes no sense? Minus infinity is not actually a number, right? It's actually just a symbol that says it's the smallest number you can ever think of. Well, clearly minus infinity is less than -2, so this should be reversed. Yes?
Is it alright if we put the answer all reals except?
Yes, we've talked about this in the past. As long as you write some sort of a sentence that makes sense. Again, you can write it in words. I don't have absolutely any problems with saying all reals except this value, or all reals except these values, or whatever. Again, the one thing that I don't want to see is, like for instance here, x cannot equal 1/3. That's not an answer. Okay? We've talked about why that's not an answer, and I don't think I need to really repeat myself. Right? Yes?
Okay, if the numerator is 24.
Like 24. Well, you have to factor it first.
Okay. Well, I factored the bottom out. I'm
Uh-huh.
not sure what I need to do at the top.
Nothing. Again, the idea is it's a rational function, which means you have a polynomial divided by a polynomial. Polynomials are defined everywhere, so it doesn't matter what the numerator is in the end. The only thing you're actually concerned about is, I can't divide by 0, so I got to make sure that I take that into account. Okay? All right. Should we move on, or do you want to see more of these?
Real quick, 25.
25. Okay, so we have f of x equals the square root of x plus the cubed root of x, right? I think they were using t's, but I guess it doesn't really matter what I'm using. So what is the domain for this function? Well, properties of functions say that when I'm looking at about this function, I'm basically looking at a sum of two functions, right? Which means whatever domain I come up with at the end has to satisfy both functions, right? But I don't have to actually take out a crystal ball and try and come up with it, from all at once. And so what I can do is I can actually take it slower. If I look at this particular function, what would the domain be for that?
0.
The idea is x has to be bigger than or equal to 0, right? How about this function? Well, as it turns out, we actually just talked about it, right? Anything goes, right? As I said, it has to satisfy both of them in the same time. So what would the domain be? 0 to plus infinity, right? Does that make sense? Again, if you choose to write it in words, you can also write it in words. You can say, it's all non-negative numbers, or all positive numbers and 0, or however you wanna phrase that. You can go ahead and do that. Is that making sense? Okay. Quickly, f of x equals the square root of 2x minus 5. What is the domain? Anybody? Yes.
Including 0 up to 5 over 2, or excluding 5 over 2. All positive, all non-negative real numbers excluding 5 over 2.
How about if you put 1?
Never mind.
So, the key idea, and this is why I actually put this problem here, especially basically I'm trying to give you a heads up as far as 26 is concerned, more or less. The key idea is, do you notice how I wrote this here? I did it on purpose. If you look at what I said in the past, I didn't say x bigger than or equal to 0. I actually just said directly that, right? When we looked at square root of x. The reason why I wrote it in this fashion is because you can't put negative numbers instead of square roots, right? Which means whatever's underneath the square root has to be bigger than or equal to 0. Well, if that's the case, why not apply that here? What I'm saying is that 2x minus 5 cannot be negative. Does that make sense? Okay, well I can work it out. This means that x has to be bigger than or equal to 5/2. Which means my domain then is just going to be from 5/2 to infinity. Does that make sense? Again, you don't have to really just jump at the answer directly. You just have to figure out what the idea is. I can't put negative numbers in here, right? That's basically what you're thinking, right? Well, why not write it? Okay? Note of caution on 26. When you multiply by a negative number, the sign of inequality changes. Does that make sense? Yeah? Okay. The answer for 26 is between 0 and 4. So if you don't get that, try and figure out why you didn't get that. And I don't have a problem telling you the answer because you're also going to be graded on actually showing work. So just by writing the answer doesn't mean you actually solved it. Okay, move on. The other two types of things that, okay, there's two more things that I want to talk about. There's a third thing in the textbook, but I'm going to skip it. That's absolute values. I think I talked about absolute values until my mouth got dry. So I'm going to switch to piecewise functions. Do you know what a piecewise function is? It's exactly what the name suggests. It's basically defined on pieces. Okay? So a piecewise function is defined. And I'll just skip the example and I'll just go to one of these problems. Let's see. How about I look at 37? Or I could do 39. '37 on page 9 says the following. F of x is equal to x plus 2 when x is less than 0. And it's 1 minus x when x is bigger than or equal to 0. Okay? This is what a piecewise function is. Okay? Basically just means it has branches. It could have 2, it could have 5, it could have 100 of them. Okay? Two questions. Or two things we have to do. Find the domain and graph it. So what is the domain of this function? All real numbers. Why all real numbers? There's two things coming into here. Number one, both of these branches are polynomials. Polynomials are defined everywhere. Okay? But also, the other thing you have to keep track of is the fact that on the right hand side here, my two conditions span over the entire real axis. Okay? If I would have had, and I'm just going to show this just for a quick example. If I would have had that, then what would the domain be? Negative infinity to minus 1 from 0 to plus infinity. Is everybody understanding this? Even though these branches are defined everywhere, I have to keep track of where my conditions are. Do you understand? Okay. So now coming back to the original problem. The domain is all real numbers. What's the graph? Well, what's the graph of x plus 2? Well, that should be an easy one, right? 1, 2, 1, 2. That would be my graph, right? So far so good? Okay, what's the graph of 1 minus x? Right? So this is y equals x plus 2. This is y equals 1 minus x. So I graphed it. I have to finish it. Why is this not the graph? This is not a function. It doesn't pass the vertical line test. Right? Is everybody seeing this? If I choose x equals 1, well, I'm going to have two values, right? This is where my conditions come into play and say, look, it's x plus 2, but only when x is less than 0, right? This is the graph of x plus 2, right? X being less than 0 means I'm looking at this side of the graph, which means I only have to take into account this piece. Does that make sense? Moreover, that point is not part of the graph. Is everybody seeing that? It's strictly less than 0, right? Looking at 1 minus x, that happens when x is bigger than 0, and so it'll be this piece. Does that make sense? Is everybody understanding how to graph piecewise functions? Okay? Yes?
It's probably a little different when it's x squared, right?
Why would it have to be different?
It's shaped.
It's going to be differently shaped. But what's the essence here? What have I done? I actually graphed both of them completely, and then I said, look, I know I have to make sure that this is actually a function. So I basically just have to look at the conditions and make sure that I meet them. Which means, if I look at a function that has a quadratic in it, then I could just probably maybe be looking at a function that looks like this, and then it has some piece. Does that make sense? I'm only taking a part of the quadratic. Let's say this would be a quadratic. If you graph it, it actually comes up. But I just have to make sure that it passes the vertical line test. Okay? Move on? Okay.
Is there times where you plug in numbers that will work with your domain, like something less than 0, something equal to 0, and then greater than 0? So I thought there was an example in the book that did that. Like that's how I started to solve 38. I don't know if I did it right or not.
The idea is, in general, you can pick up points if you want. But notice all these problems involving piecewise functions, 37, 38, 39, 40. At the most, you have a quadratic function. Okay? Which means you should be knowing what the graph of a quadratic function is. And I'm saying you should be. I'm not saying it in the sense that if you don't know it, you don't belong here. But the point is, we've talked about it, so it shouldn't be strange to you to graph a quadratic function. So yeah, you can pick points if you want, but in the end, you should know how to graph a linear function, right? Because all you have to do is basically look at either, if it's written in this form, you look at the y-intercept, and then you basically just look at the slope, so you can graph it. And then if it's a quadratic function, again, you should be able to graph it relatively easy, because it's just x squared or whatever the situation may be. Yes?
So if there's when it says x is greater than 3, do you start at 3 or do you start greater than 3?
You start at 3, but you just have to make sure. See here, I technically started at 0. I just have a little hole in there because this point is not part of it. But yes, technically I graphed all the way up to when you put 0 in for x, you end up with 2. But if it's strictly, that means the point is not part of the graph, so I just basically put a hollow circle. Okay? Alright, the only other topic in this class, or in this section, that we're going to cover is, I'm going to skip through, I'm just going to verbally say things. Do you know what a definition, what does it mean for a function to be increasing? It means it keeps going up, right? Graphically speaking. What does it mean for a function to be decreasing? Goes down, right? Does that make sense? We're actually going to come back to these definitions later on. This is kind of like more or less verbally. However, the one thing that I do want to stress about, especially considering when we're actually going to get to graphing, the way the progression of the semester works, and again, I kind of got caught in this pre-test, and I haven't really talked about too much about what we're actually going to be doing in calculus. We're going to have 3 major topics in calculus, and one basically is going to lead into another. First topic is going to be limits, second topic is going to be derivatives, and the last topic is going to be integrals. Okay? Derivatives is going to be the part of the class that we're going to spend the most time on. Okay? Limits we're going to spend a little time, then we're going to go to derivatives. We're going to develop what a derivative is and everything else, and ways of taking derivatives of functions and everything else. The key application of that is going to come in the next chapter, where we're actually going to be dealing with graphing functions. We're going to spend a lot of time graphing graphing rational functions and finding asymptotes and all this fun stuff. And so we'll come back to graphing a lot, and so we're also going to come back to increasing, decreasing. But one of the things that we're going to find quite useful as far as graphing is concerned is the concept of an odd or an even function. Okay? Do you remember what an odd function is? Do you remember what an even function is? What is an odd function?
Symmetry, point symmetry?
Point, but it's actually at a particular point. At the origin. Symmetric towards the origin, right? So let's see. A function is odd if so this is where I want to stress things out. Graphically speaking, a function is odd if it's reflected towards the origin, right? If it's symmetric towards the origin. But as I said, what we're going to do is we're going to try, here's a function, now try and graph it. So if I don't have the graph, how would I know if the function is odd or even? If f of minus x is equal to minus f of x, that's when a function is odd. Okay? A function is even if f of minus x is equal to f of x. A function is even if it's reflected over the y-axis. Now, there's a lot easier way of remembering these. Yes?
Isn't it like the leading term is usually leading powers is odd or even?
Yes. The very simple way of thinking about things is think about polynomials. Think about power functions. Right? F of x equals x. It's a linear function. Right? If I put in minus x, well, I end up with minus x, right? Which means if I put in minus x, I end up with minus x. That means my function is odd. Right? It is not coincidental that all the odd powers of polynomials will actually be odd functions. Does that make sense? Why? Because negative to whatever odd power comes out, and so you'll have this property, right? Even functions, we'll think about x squared. If I put minus x, right? If I look at f of x equals x squared, well, f of minus x is just going to be minus x quantity squared, but that's just x squared, right? Which means my function is even. Again, it's not coincidental that my power is in fact even. Okay? So it's very simple to figure out if a function is even or odd as far as polynomials are concerned. Now, is f of x equal x squared plus x minus 3 odd, even, or neither? Neither. Why neither?
Because if you plug it in, the x squared remains x squared, but the negative x becomes minus x.
Exactly. X squared is an even function. Negative 3 is an even function, but x is an odd function. Right? So when I replace x with minus x, I'll end up with x squared minus x minus 3, which will not be either f of x or the negative of f of x. Is everybody understanding this? In general, if you add an odd and an even function, your function is going to be neither. Or neither. I guess it depends on how you want to say it. Is it neither or neither?
Depends on your accent.
Depends on your accent?
Yeah.
I see. The English language is a wonderful language that sometimes makes no sense. Okay, so as far as polynomials are, it's not that hard to figure it out. Okay, let me ask you a question. Can a square root or a fourth root or a sixth root ever be odd or even? Square root of x, fourth root of x, sixth root of x, and so forth. Can these be odd or even? No. Why not? Well, if you talk about graphically speaking, and think about trigonometric functions, all of these are actually going to be, their graphs are going to be exclusively in the first quadrant. Do you understand that? You can only put positive numbers inside x, inside the square root, which automatically forces you to the right side of the graph, right? Moreover, the square root of any of these is a positive quantity, which means it'll put you above the x-axis, right? Which means you're in the first quadrant. Well, think about reflections. How can I reflect over 0 if I'm just in the first quadrant? How can I reflect over the y-axis again since I'm actually only in the first quadrant? Is that making sense? However, cube root of x ends up being odd, right? Because minus x quantity, the cube root of minus x is just minus the cube root of x, right? Okay, so as far as these are concerned, it's relatively easy. How about f of x equals sine of x, f of x equals cosine of x? Sine is an odd function, cosine is an even function. What would that make tangent? Actually, they're both odd. Tangent and cotangent. Why are they odd? Well, one way of thinking about it is obviously if you want to think about graphs, right? But there is a much simpler way to think about this. Think about tangent of minus x. This is just sine of minus x over cosine of minus x. Right? What is the property of odd or even? For the even, the minus disappears. For the odd, the minus comes out. Right? Well, this is just going to be minus sine of x divided by cosine of x. Right? Which is just minus tangent, which means the minus comes out. Right? As it turns out, if you multiply an even function by an even function, you end up with an even function. Why? Because technically plus times plus is plus, right? Think about odd as being minus, right? If you take a minus and add, multiply it or divide it by a plus, you end up with a minus, which would be the situation. If you take out a minus and divide it by a minus, you end up with a plus. Does that make sense? Which means if you multiply two odd functions together, you actually end up with an even function. Is that making sense? Yes?
Okay. What if you had sine of negative x divided by cosine negative x? Wouldn't that be the same as sine of x divided by cosine of x? Because you have a negative on the top and the bottom.
This is the argument of sine. This is a function. Sine of minus x. This minus cannot come in front unless you actually have some a priori knowledge of the fact that the function is odd. We just said cosine is even, which means cosine of minus x is in fact cosine of x.
Oh, okay.
You have to be careful with functions of expressions. You can't just take things out just because it might look like you can. Like for instance, and maybe this would be a very good time to come up and say that, cosine of the quantity x squared is under no circumstances cosine of x quantity squared. Is everybody understanding this? Yeah? Okay, so let's move on to section 2 then. And I'm not going to spend too much time on this because we actually just talked about it. We talked about polynomials, right? We talked about rational functions, and we talked about trigonometric functions, right? So there is really no point in me spending time, or I don't think there should be any point spending time talking about the catalog of functions, because, as I said, we pretty much covered every single one of them, unless you have a particular question. A polynomial just basically says, everybody knows what a polynomial is? The general form of a polynomial, maybe I should just say that. The general form is, let me write it in descending order. An x to the n plus an minus 1 x to the n minus 1 plus so forth plus a1x plus a0. This is the most general form of a polynomial, where n is the degree of the polynomial, so n is the degree of the polynomial, an is the leading coefficient, and I guess ANX to the n is the leading term. To talk about definitions. Is this making sense? And again, this is something that I actually, if you haven't seen this before, I actually talked about this when we were talking about quadratic functions. I kept referring to the number in front of x squared as the leading coefficient. Remember this? So if you haven't seen it before, I guess I, talked about it anyway. So this is the general form of a polynomial. As we said, rational functions are just going to be ratios between these two, and between two polynomials and so forth. Okay, let's see. The next topic about functions is a topic I'm basically going to skip, because I spent, I think this was on Friday, when we talked about the pretest, and I was looking at exponential, it was logarithmic functions. I talked about what happens when you put a minus inside, or when you put a minus outside, when you add a number inside, when you add a number outside, right? That's basically what this would basically be, the vertical and horizontal shifts. And I just talked about that, right? With the minuses, you get reflections. If you add inside or out, you get shifts, right? If it's outside of the expression, it shifts up or down. If it's inside the expression, then it shifts left or right, right? The only other thing would be the stretching and the stretching, but I'm not going to spend any time on that, right? So just think about what happens if you multiply it by 2. Well, your function is actually going to end up, well, I guess stretching up, right? Technically, it looks like it's stretching, it's shrinking, but in reality, it actually stretches up, right? Think about the graph of x versus the graph of x of 2x. Well, or I guess that's not necessarily that interesting to think about, but just basically think about the fact that instead of the y value being a certain value, now it's actually twice as that, which means it actually stretches up, right? But that's something that I never really cared about too much, so we're not really gonna, well, not that I didn't care about it, but I don't necessarily want to spend too much time. The one thing I want to bring up, and again, this is a concept that all of these concepts you actually have done in pre-calculus. I just want to make you basically cover things just to be as a refresher. The next topic, and I want to spend some time on this, is composition of functions. Do you remember what does it mean for two functions to be composites? To compose one function with the other? And you can say no. The little circle. The little circle, yes, f of g of x. Okay. Definition. Given two functions, f and g, the composite function f little circle g, or otherwise known as fog, is defined by fog of x equals f of g of x. So, I guess before I go there, let me just ask one thing, and this is because you have one problem like that in the homework, so I want to make sure that you actually know how to do this. Problem 35 says, here's f, here's g, come up with f plus g, f minus g, f times g, and f divided by g, and find all their domains. Is there any point in me spending time on that? Remember what we talked about domains. I had that original function in section 1 that was the square root of x plus the cube root of x. And I said, if you think about the domain, think about them as being two individual functions that you add up, and their domain has to coincide. Right? That's exactly the idea here. right? If I have my f, I have my g. Well, if I add them together and I ask you for the domain, it's obviously the joint domain between f and g, right? Does that make sense? Similarly for f minus g, similarly for f times g, similarly for f divided by g with one condition. What would be the condition? Can't divide by 0. G cannot be 0. Is that making sense? Yes? Okay. So now let's see. Do you want me to do a problem in particular or just pick some random one? I'm looking at problems between 37 and 42, which says here's f, here's g, come up with fog, goff, foff, and gog. $37, $39, $41. Should we start off slowly with a 37? Since you all seem to remember so vividly composition of functions. As it turns out, composition of functions is going to become something very important to us as far as this course is concerned. Especially when we get to derivatives, and later on, right at the end of the semester when we talk about integrals. So let's see, f of x equals x squared minus 1, and g of x equals 2x plus 1. So what is f composed with g of x? Also known as fog. So by definition, it's f of g of x. Now, if you haven't gotten used to this, or if you don't remember exactly what this is, take it an extra step. Write what g of x actually is. This is nothing else but f of 2x plus 1. Right? What do we learn about functions? Whatever I have in parentheses, I have to replace with whatever I had for x. So this is just going to be 2x plus 1, quantity squared minus 1. Does this make sense? Yeah?
Yep.
Okay, what is the domain of fog? All reals, right? Okay, how about 39?
Oh, wait.
Yes.
Same thing for like the g of f, goff, wait a second.
You want me to do the other ones too?
I'm a little confused because in the previous problem we had f times g, and then we had f divided by g, f plus g, just as simple. Okay.
Those are just simple operations. Yes, you just basically take one function divided by the other, and so forth. The composition is where you actually, the idea is you apply it as f of g. So the idea is that you're plugging in another function in terms of x. Yes?
For the last equation, do you want us to completely solve it out, or can we leave it?
You can leave it like this.
Oh, really?
You can leave it like this, but sometimes, we're going to go through 41, and that you'll see that we actually have to go ahead and solve it. Simplify it. And the whole idea is, I don't necessarily care, this is okay by me, because the next question is, what is the domain? And so just by looking at this, I know this is a polynomial, so there's really nothing that working out the algebra is not going to change my domain. But there's problems in which you actually have to go ahead and do the algebra to figure out if you actually have the correct domain or not. Okay? Now, domains of composed functions are actually a little tricky. And I'll give you an example why. So let's look at 39. I guess we have 15 minutes, so that's good. Okay, so let's look at 39. I have f of x equals sine of x. And then I have g of x equals 1 minus the square root of x. So, before we go any further, what is the domain of f? I'll just write it as sometimes want to write less words. So would that make sense that it's the domain of f?
Yes.
Okay, so what is the domain of f?
Real numbers.
All real numbers. What is the domain of G?
Everything is 0.
So everything from 0 on, right? Okay. So now what is fog? And what is gof? So it's f of g of x, which again, if you're not, very fast with these things, just replace what g is first. That way, it should make your life a little easier later on. So f of 1 minus the square root of x. So it's just sine of the quantity 1 minus the square root of x. Right? What is the domain of f composed with g? 0 to plus infinity, right? Okay, how about g composed with f? It's going to be g of f of x. So it's g of sine of x. So it's going to be equal to 1 minus the square root of sine of x. What is the domain of this? Bless you. Sorry? What is sine of 3 pi over 2? Negative 1. Square root of negative 1 does not exist. So what do we have to do? We have to have sine of x be bigger than or equal to 0. Right? That means x has to be between 0 and pi. But do we stop here? No, because sine is periodic of period 2 pi. So this is going to be union 2 pi, 3 pi, and so forth. How do you write it?
C means integer, right?
Yes. Last time I wrote it, everybody was confused, so I said I'll write it in words this time. This is how you write it. You say, do you see that I'm basically creating all the intervals in this fashion? Right? Because when k is 0, I end up with 0 to pi, which is the one that I have. When k is 1, I end up with 2 pi, 3 pi, and so forth, right? I could have wrote this as 2k plus 1 multiplied by pi, which is actually what I wanted to write. But I wanted to write it in this fashion so you can explicitly see that it's the original quantity I started with plus a pi, because the length of all of these intervals is pi. So that's why, I wrote it in this fashion. Is this making sense? Yes.
How would it work if it was cosine?
Well, when is cosine positive? Think about this again. Sine of 0, 0. That's how I think about it, which means cosine of 0 is 1, right? 1 means I'm at the height, which means I need to go left and right of it. So it'll be minus pi over 2 to pi over 2. Does that make sense? Again, remember, personally, I don't like to memorize things. So when I said that all I always think about, everything that I always start with is sine of 0 equals 0, you probably thought I'm crazy, but literally, that's what I think about. Because if that's 0, then I know cosine is 1, and then I just basically pick it up. So when you ask me, how about cosine, I actually just went through that in my head. I figure, okay, sine of 0, 0, cosine is 1, I gotta go left or right of that. That's the answer. Is that making sense? Okay, 41 is one I really wanted to get at. Oh, actually, let's see. How about GOG, or otherwise known as G composed with G of X? So it's G of 1 minus the square root of X, which equals 1 minus the square root of 1 minus the square root of X. Fun? So what is the domain of this function? 0 to infinity? 1 to infinity? Okay, to counter example both of you, what happens when you put 4 in? You get the square root of -1? So what has to happen? Two things have to happen. The square root of X, sorry, I shouldn't say that. Yeah, actually that's fine. Let's start it off. If I look at the square root of X, X has to be bigger than or equal to 0, right? If I look at the square root of 1 minus the square root of X, what has to happen? 1 minus the square root of X has to be bigger than or equal to 0, right? When is 1 minus the square root of X bigger than or equal to 0? This means that 1 is bigger than or equal to the square root of X, right? Which means, depends on what you want to do, and you have to be careful about this. If I'm squaring both sides, I'll end up with actually X being between -1 and 1. But in reality, I can't have negative numbers inside of square roots. And so this means that X is between 0 and 1. Right? Does that make sense? The above condition tells me that X has to be between 0 and plus infinity. If you look at both of them, what do they have in common? 0 to 1. Does that make sense? Everybody sees that? Again, notice what I've done. You don't have to just look at it and, hoping that if you stare long enough at it, the answer will jump at you. The idea is just take it on steps. What do I know? What are my conditions? Well, first of all, I have a square root of X here, so that means that X has to be positive, right? Or non-negative, I should say. Second of all, this quantity inside the square root has to be positive. Well, let me just work out what that means. So I basically just write that out, and I work out and come up with the answer. Does that make sense? Okay, 41, which is what I wanted to really get at. We have f of x equals x plus 1 over x, and g of x equals x plus 1 divided by x plus 2. So, what is the domain of f? What is the domain of g? All reals except 0, and all reals except -2. Right? Did I use this notation before? Well, I guess I used it now. Does it make sense? You're looking at all real numbers, you take out 0. Right? You can also write it as -infinity to 0, union 0 to infinity, right? Okay. What is g composed with f of x? We do have 5 more minutes, right? Okay, so what is g composed with f of x? It is g of x plus 1 over x, right? Which equals x plus 1 over x plus 1 divided by x plus 1 over x plus 2. So what is the domain of G composed with F in all its splendor. I heard a word and I want to make sure nobody actually does that. You can't cancel anything. There's no product. Right? I can't say I have 1 over x here, 1 over x here, I'll just cancel out and move on. Because they're all added, they're not multiplied. So what is the domain of G composed with F? Well, clearly the only way I can answer that is, yeah, I'm looking here and I'm saying this can't be 0, right? Well, what does that mean? So this is what I said. I might not necessarily say it explicitly as in the fact that you actually have to work out the algebra, but you have to work out the algebra to come up with the answer. So what happens if I multiply and divide by x over x? What do I get? What do I get in the numerator? X squared plus 1 plus x. What do I get in the denominator? X squared plus 1 plus 2x. So what is my domain? This becomes x squared plus x plus 1 divided by x squared plus 2x plus 1, which equals x squared plus x plus 1 divided by x plus 1 quantity squared. So what is my domain? All reals except -1 and 0.
Could you set the bottom equal, the denominator equal to 0?
Yeah, that's where I got the -1 from. Right? You get x plus 1 quantity squared equals 0. Means x plus 1 is equal to 0. Means x equals -1. Right? Why 0? Remember what I started with. This is my composition. I'm dividing by x here. If x is 0, this doesn't make any sense. Moreover, it's very easy to say, oh, I'm multiplying and dividing by a quantity. What is this entailing? That this is not 0 over 0. Otherwise, I can't multiply and divide by 0 over 0. It doesn't make any sense. Right? So in this step, I'm basically assuming already that x cannot equal 0. Now you might ask yourselves, this is kind of hard. How am I supposed to remember that I have to keep adding this 0? There's actually a reason why I asked you for the domain of f and the domain of g. The domain of f says it's all reals except 0. Right? When I look at my composition of functions, I'm looking at g composed with f. Two things have to happen. First of all, f has to make sense, which means x has to be in the domain of f. Second of all, g of f has to make sense, which means I got the -1 because g composed with f has to make sense, and I got the 0 because f has to make sense. Does that make sense? Which means when you do these type of problems, you come up with whatever expression you have at the end, you look at the domain of this expression, and you make sure you test it against the domain of f. And you have to come up with the joint domain of both of them. Does that make sense? Okay. One more thing. 45 on 23. And I'm just going to say this. You actually have a problem of this nature in your homework. Capital F of x is x squared plus 1 to the 10th. Can you come up with f and g so that f composed with g of x is in fact equal to capital F of x? This is really what we're actually going to get at as derivatives are concerned. So can I come back, can I break it apart into two functions? And the answer is yes, relatively easy, because fog is just f of g of x. Which means what we're actually interpreting is that g is an inside function. Which means if I look at g of x as being x squared plus 1, and I look at f of x as being x to the 10th, then f composed with g gives me my original function. Is everybody seeing this?
That's everything you just learned about, right?
Yes. Everything we've learned backwards, and this is actually what we're really going to be using in derivatives. The point is, can you break it down into functions? That's actually what the ultimate goal is going to be. Okay, we'll stop here. Homework is due on Wednesday. So the first 2 sections are going to be due on Wednesday. If you don't have the homework sheet, I guess it's also on the website. And I actually updated the syllabus online, since I had two problems there. First of all, I said the final exam was Monday, and in fact it was Wednesday. I had the correct date. I just had the wrong word. And then also I said homework is collected on Monday. It's written on the syllabus, but in reality on the homework sheet, all the homework is due on Wednesday. So I just changed that. I'm not going to print out a new copy and give it to you. If you want to print out a copy for yourselves to have the new things, you can.